Now that we've learned how to graph the parent exponential, let's focus on how to graph the parent logarithmic function. I will say you can utilize a calculator as long as you understand the change of base rules to determine your y values. And what I mean by that is, as we get ready to identify x's, instead of doing it algebraically, you could stick those x's into the log function and have the y spit out that way. But again, you have to be really careful about that because it will require you to use a change of base functionality on the calculator. What I'm going to do is show you how to graph it by hand, again using the concept of a t-chart. So just like the graph of the exponential, to graph a log, I have a preliminary t-chart set up here where I'm going to be choosing some x's and seeing what happens with y. I do want to point out that just like we were choiceful on what we selected for x in the exponential example, we're going to be very choiceful about what we choose for x in the logarithmic example. In fact, I would argue we're going to be even extremely more choiceful, and I'll explain what I mean by that. But first, let's remind you of what the logarithmic function looks like. So this is a typical logarithmic function. So we have f of x, or y, equals the log of x to the base b. Where the x is, that's the argument of the log, and x is our independent variable. Those are going to be the where we're going to select some x's and we're going to stick them right there. B, again, is just some number, and again, similar to the exponential, we have restrictions. It has to be greater than 0, and it cannot be 1. And so just like the exponential case, you can see I've put this example here where we're going to graph the log of x base 2. But I could have chosen base 3, base 4, base 5. So each base will yield a slightly different logarithmic parent. They're all going to have the same general shape, just the slope of the curves might be off slightly depending on what we choose for that number. Okay, so what do we pick? One thing I need to call out is the argument of a log. This is actually a new domain restriction rule that you may not have learned up until this point in your studies. But the argument of a log, it cannot be negative and it cannot be 0. That does not exist. So whatever is inside this argument, it has to be a positive thing. It can be a fraction, can be a whole number, can be an irrational positive number. Cannot be 0, cannot be negative. And so as we get ready to select choices for x, we need to make sure that they're bigger than 0, number 1, okay? And that does lead to, I'm going to go ahead and write it in now, the domain of parent logs, it is 0 to infinity. So we have to choose x's that are bigger than 0, okay? Now, what are good choices? This is where you have to be really careful if you want to do this by hand. And this log rule over here I have written in red. This is what's going to help you out here. If you remember from the study of log rules, if you have an expression that's the log of b to the n, where that's some number to a power, and that power can also be a number, and it's to the base b, if the base and the argument, if those match, then the value of that entire expression right there is actually equal to the value of that exponent. In other words, n. And so if we remember this log rule, it actually helps us make very, very wise choices about what to pick for x so that we can do this by hand. And what I mean by that is, if you notice this problem, the base that we're doing is a 2. So look very carefully at each of these choices for x. I have 1/4, 1/2, 1, 2, 4. Well, if you look really carefully, those are all powers of 2. So great choices are, we are going to pick numbers that are powers of 2. And so for example, the number 1, that's 2 to the 0 power. The number 2, that's 2 to the first power. The number 4, that's 2 squared. But let's also choose some fractions. If I take 2 to the negative 1, that's actually 1/2. Or 2 to the negative 2, that's actually 1/4. So by choosing these values for x, and again I have chosen 5 to try to make sure I have a good representation on the graph. By choosing powers of 2, what we're really sticking in for the argument for x is actually 2 to a power every time. And remember, when you stick something into a power and that argument and that base match, that's actually the answer that spits out, or your y, in other words. So when I put 1/4 in for x right here, because that's actually 2 to the negative 2, the y value actually equals negative 2. And likewise, when I put 1/2 in right here, that's actually 2 to the negative 1. So that power again, that's my answer. So y would be negative 1. 1 is 2 to the 0, so the y value is 0. 2 is 2 to the 1, so my y value is 1. And then again, I'll write this one out. When I let x be 4, that's actually 2 squared, and so my y value is 2. And so it is a very slick way to be able to graph these guys by hand. So again, I can't stress enough, whatever parent log you want to graph, your choices for x should be powers of whatever the base is, and great powers would be these, the negative 2, negative 1, 0, 1, and 2. So if we take each of those ordered pairs and graph it, we can see what the parent exponent, or parent log, excuse me, is going to look like. So when I let x be 1/4, you know, that's about right here. The y value I got for that was negative 2. So that's down here. When I let x be 1/2, so that's right here. The y value I got was negative 1. When I let x be 0, excuse me, when I let x be 1, the y value that I got was 0. So that's this ordered pair right here. When I chose an x of 2, the y I got out was a 1. And then finally, when I let x be that 4, the y that I got out was a 2. So if you very carefully plot that, you start to see that logarithms take this general shape. So they all start out down here, the y values start down at negative infinity, and they very, very, very quickly climb. They all go through this point at 1, 0, and then they curve, and then they eventually taper off. So a general shape for a log will look like this. And again, because we are not allowed to have anything that is 0 or negative for that x, we do end up with an asymptote line here again, because this function only exists for positive x's. So if I draw this asymptote line, it is a vertical asymptote. It comes right along like this, and that's actually the y-axis. So here is that vertical asymptote that my function does not cross, and it's actually the line x equals 0. So again, all log functions take this general shape, the parent functions. They're going to start down here, they're going to climb, 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 cross through the point, 1, 0, and then curve and then taper off. They never do become constant, but as x approaches infinity, that y value does start just very slowly climbing. So it might look like it's becoming constant, but it does not. Each successive x does cause a higher y. It's almost invisible to the eye after a period of time. Okay, so that is in general how you graph an exponential. What I did want to call out quickly is that I happened to choose examples where the base was 2 in both examples, but what if I had chosen something else? What if I had chosen a base of 3? Well, you can see I took the time, I already graphed that new curve on here. What happens is, as this base gets bigger, we'll notice that it still has that same shape of an exponential where I'm hovering above the x-axis, I approach that y-axis, I go through the point, x is 0 and y is 1, and then I shoot up. Well, as this base increases, what you'll find is that as you hit that important point right there, the 0.01, after you hit it, the higher this number, the more quickly you turn and advance up. So if I had chosen a smaller number, then I would have had a more gradual increase. Same for the logs. Because this was a base 2, this was what the slope of that curve looked like. But if I had chosen a 3, for example, and had graphed the log of x base 3, again, I would have seen that same characteristic starting down here at negative infinity. I would have come through the point 1, 0, and then I would have more quickly tapered off and started So I would have more quickly kind of made that turn and started to taper off. So that's the only difference that you see. As this base changes, it doesn't change the general shape of the curve. What it does is it changes how quickly you start to turn and have that exponential increase or that logarithmic stability that you start to see. The last thing I want to point out is these are just the parent functions. So we can also do transformations on these functions, and so that will be actually a separate video where we'll take a parent and talk about how we can move that function around. So just like other transformations for other parents, we can move it left and right, up and down, we can reflect it, we can do stretching and compressing. So that will be the topic of the next video. But in order to understand transformations, you really need to understand what the basic parent functions look like first. So I hope that this was helpful.